Now, it is my pleasure to introduce today's speakers, Professor Moncef Krarti and Dr. Nick Clements. Moncef Krarti is a professor in the Architectural Engineering Department at CU Boulder and Executive Director of the BEST Center. Professor Krarti has experience in designing, testing, and assessing innovative energy efficiency and renewable energy technologies applied to buildings. He has also directed several projects in designing energy-efficient buildings with integrated renewable energy systems. He has published over 250 technical journals and handbooks, chapters in various fields related to energy efficiency, distribution generation, and demand-side management for the built environment. Dr. Nick Clements is the manager of the Larson HVAC Laboratory in the Architectural Engineering Department at CU Boulder and manager of the BEST Center. Dr. Clements' research experiences include indoor air quality, airborne infection control, and healthy buildings. He has served as the ASHRAE Environmental Health Committee Chair and as a voting member of multiple ASHRAE committees, including SGPC 10, Interactions Affecting the Achievement of Acceptable Indoor Environments, the Position Document Committee for Health and Wellbeing in the Built Environment, and the IEQ 2025 Conference Organizing Committee. Professor Krarti and Dr. Clements, thank you for taking the time to share some of your work with our alumni and friends today. I'll go ahead and hand it over to you.
Thanks, Ellie, for the introductions, as well as for the opportunity to reach out to our alumni to let them know about what's happening, at least in our program. So our presentation today will focus on the architecture engineering program within CU and some of its research activity, as well as two programs that we want to let our alumni know about. As you may know, architecture engineering is actually one of the, first program in the U.S. created at the CU in 1925. It was created, and the first award was in 1929. Actually, these days, CU is one of almost 300 programs focused on architecture engineering and building engineering in general in the U.S. alone. Throughout the world, there is thousands of programs. The architecture engineering at CU is actually have a 3-degree, a Bachelor of Science, Master of Science, as well as PhDs. And there is only a few, maybe around 12 architecture engineering programs in the US that offer this 3-degree. So our program focus, as the name said, on the building systems, as well as the design, retrofit, and operation of building system in general. Today, we'll focus on the energy system for buildings. So we want to present some research activity in the architecture engineering, as well as two programs that we hope our alumni will either connect with these two programs or at least share the information with others so they can be connected to both the BEST Center and the Renew America nonprofit Rocky Mountain regions. First, I will focus on the highlight why we are actually looking into building energy system per se, and focus on a couple projects, at least to have an idea what we are doing actually in terms of improving the energy efficiency of buildings. So first, I'll focus on the reason why we are interested in building. Obviously, everyone know that we spend a lot of time indoors. Before COVID was around 80% or so. And building, typically in cities, 20% of people in the 90s used to live in cities. In 2010 is 50%, at least worldwide. And in 2030, it's expected 60% of all world population will live in urban area, where obviously buildings are prominent. In addition, as you know, building consume a lot of energy. In the US, 39% of total energy consumption is attributed to buildings. And as shown in that chart, US buildings consume a lot of energy compared to other buildings in the world, either per square footage or per persons. in addition to the total energy consumptions. Most of the energy is consumed by heating, cooling, as well as ventilation, more than 50% in the US commercial building based on Department of Energy surveys. Obviously, buildings also responsible for almost more than a third of US greenhouse emission and carbon emissions. In terms of electricity, 75% of US electricity is used in building sector. So that's why we are interested, at least as a program, to try to make some changes about the energy performance of buildings. Since the built environment affect other areas in addition to the obviously energy consumptions and carbon emissions, it affects the indoor and outdoor qualities, obviously for occupant as well as their productivity. In addition, it will affect the availability of material and resources, in addition to the ecosystem and environment. We are, these days, we are trying to account for all these impacts using another metric, I guess, that's been around in microeconomics. We call it energy productivities. And we are trying to, in a way, improve the energy productivity of building through energy efficiency, as well as using some other technology that I'll highlight today, at least briefly, in part of our research activity in the architecture engineering program at CU. Some of these technology is related to what we call sustainability, intelligence, and resiliency of buildings. So we think future of building will need to be sustainable, adaptive to changing of the environment, and resilient because of the climate change. These type of building will obviously improve the energy efficiency, reduce the operating cost of building, add value to the property, either rental value or resale value, enhance the safety and security of occupant, as well as it can be easily integrated within the systems, for instance, a smart city and smart grid. So obviously to achieve that, there is different initiative. Some of them are sponsored by Department of Energy as well as others organizations. For instance, grid interactive efficient buildings. We obviously connected to what we call grid connected communities, microgrids, which rely on several other programs, for instance, electrification, decarbonization, and making building and community more resilient. Today, I'll focus mostly on the first one, how we make building more grid interactive and more dynamic, and I'll discuss a couple technology we're working on. So by definition, grid interactive efficient buildings, a building that interact with the grid, so they have to have the capability to reduce its energy use, has the capability to shed some of the load or shift some of the load and modulate the load as well as generate energy. In a way, it tried to respond to the need that availability of energy now is intermittent. It's variable because we rely more and more on renewable energy like solar or wind, which are not constantly available. They're variable. So we try to make the load of the building adapt to this variability of, in a way, energy. So there's a lot of technology that some of them are already available and some are being developed. For instance, I'm sure you heard about smart thermostat or smart meter, as well as commonly known as smart glazing or smart windows. But there is other technology being developed by universities, including ours, to try to make building more dynamic, more adaptive to the exterior environment. Some of these are related to the building envelope. So we try to make the building envelope rather static, and as it is currently now, to be more dynamic, more adaptive, which obviously involve some control and some other materials as well as systems that are currently available. So some research being done at CU involving breathing materials as well as a double skin facade, phase change materials, application to building envelope, dynamic insulations, dynamic cool roof, as well as smart shading devices. I'll only focus on a couple of these for today's presentations. The concept, relatively new concept of what we call dynamic insulation systems. So we have a prototype and a patent related to this technology, which stem from the idea of shading devices, louver systems, where the actual insulation could be placed in a layer in a louver that could be movable, similar to shading devices as shown at least in the animation here, as well as we built the prototype and we did some testing in the lab. The lab results show that indeed by moving or at least rotating these louver of insulations, we get variable R value. For a given, for instance, angle of inclinations or the placement of these insulation, we have a different R value that vary between high level to a low level. And that's what the research show, that having dynamic insulation is actually suitable for climate where there is variability in terms of the weather as well as temperature outdoors. So for instance, in Colorado, we know that during the night, even during the summer, it's very cool. So it will be a good idea to have a low insulation during the night so we can let cool air, or at least coolness, cool energy go inside and we release the heat that it's kept inside to outdoor. And then during the day, we can refer to the high level of insulations so we can reduce at least the heat gain from hot outdoors to the cool indoors. And we did a few analyses throughout the US about the at least the energy performance and the benefit of these dynamic insulations for residential as well as commercial building for the US. So for commercial, for actually in this graph, I show the residential building. What is the potential energy saving throughout the US related to heating, cooling systems? As you could see in Colorado, for instance, we could actually save up to 30% of the energy needed for heating and cooling relative to high R value static insulation systems. In California, especially in San Francisco, we could reduce this energy required for heating and cooling by up to 45% just by having these dynamic insulation systems. In other technology, in a way similar, related to building envelope, but attachment to the window, it's an overhang that it's dynamic. So it has actually two function to provide shade as well as to provide a space for a PV to be placed on, especially if you don't have enough space in the roof. So with these dynamic shading devices, we can operate them to actually provide both the needed shade during the summer as well as generate electricity using PV. So the operation of the system could actually controlled to optimize both the shading benefit as well as the electricity generation benefit. We did some analysis for a few buildings, at least residential as well as commercial, for different location in the US. And we found, especially for hot climate like Phoenix, we could achieve almost net zero energy if we adopt this technology for all the window in a house, okay? We don't need any additional, at least measure to achieve that net zero, at least the design. We went even further and tried to use just these two ideas of what we call dynamic envelope systems. We integrate them together in office building. So we obviously using what we call also adaptive envelope systems. So in addition to the dynamic insulation I mentioned, that we can deploy either in the wall or in the ceiling or the roof. And even we can adopt this technology in the floor. So we have a variable and dynamic insulation level. We have what we call dynamic window or smart glazing in a way, switchable glazing with different tint as well, different R value. In addition to PV integrated overhand that I mentioned before. So with the right control, what we call the optimal control, we could actually combine all these technology and achieve not only a net zero energy, but positive energy. So with the electricity we generated on site, both in the overhang as well as at the roof, we could achieve more or offset more than 100% of the energy consumptions of the building, the office building itself. Which lead us to say that by integrating all these technology, we could actually achieve what we wanted, building that could be adaptive, meaning adapt to the environment, as well as be not only consume relatively less amount of energy, but even produce more energy than it's needed. And that's what we think the future of building will be. With this, obviously, comes the control. So to adapt these building envelope, we need some control mechanism that make these measures effective. And that's why there relies on smart building with these type of technology. So it's, we can save both in terms of energy consumption, but also on peak demand, as shown here with the integrated adaptive envelope systems. This activity or this type of technology is part of at least effort to improve the design of a new building, but also it could be adapted for existing building. In fact, our program also is involved in research activity related to improving the performance of the existing building, because we think, especially in the US, 95% of the building already exists. We need to improve at least the performance of the existing building if we want to achieve by 2050 net carbon at least economy, especially for the building sectors. So one of these activity is actually developing what we call automated energy audit tool. So energy audit, as you may know, it's one step to try to determine what's the best energy efficiency measure or retrofit measure before you implement them and do the actual execution to retrofit the building. So this energy audit process is rather lengthy in general. If you want to do the second level, at least level 2 energy audit, you need to have energy model that it's calibrated, that match actually the reality. Typically, we use the utility data, the monthly utility data, to ensure that the energy model mimic the reality. In a way, we are trying to develop some kind of a digital twin or model of a building before we determine what's the best energy efficiency measure to implement for specific building. So this tool allowed to make this process of calibration as well as determining what is the best energy efficiency measure automatic, okay? And that's the tool that we are actually developing as well as testing through another program that I will talk about it later in this presentations. So this tool has been checked or at least demonstrated using a house in Boulder, Colorado, where we obviously have a basic information from initial walk through, and then based on this information, we built a model. At least we used the tool. The tool was able automatically to calibrate itself and match at least the monthly energy consumption from the utility data, as shown here, for both electricity and natural gas on a monthly basis, as well as developing what should be the measure, the retrofit measure needed to electrify this house. We found through optimization that we can electrify the house and save about 49 or so, 48% actually of the energy consumption relative to the baseline. So with this tool that we will try to actually demonstrate in the other program that I'll mention about, will be available hopefully online as part of our at least outreach to the community. With this, I'll let Nick introduce the first program that we want to inform you about, the Building Energy Smart Technology Center.
All righty. Thanks, Moncef. Yes, so I am managing this center, and Moncef is the executive director. So I'll be digging into what the BEST Center is. To start off, I'll describe the model we're using to operate the center. So it's a project through the NSF called an Industry University Cooperative Research Center. And the goal of IUCRCs is to combine the strengths of government, university, and industry to produce cutting-edge research. Ideally, the topics are kind of on the edge of commercial readiness, so we can kind of take projects that faculty have been working on, pair them with interested industry partners, and get those projects over the line to be commercial. We have an industry advisory board that I'll show later, and this board annually contributes fees to the research center, and those fees go into research directly. NSF only pays for operation management costs. So our industry board directly fund all the research that happens through the BEST Center. We're about halfway through our first phase with the NSF. So the center, the phase one will go through 2026. We've distributed about $865,000 in funding in the last 3 years. We have 5 projects funded this year. It's a collaboration between CU Boulder and City College in New York. And we work closely with University of Albany, faculty there who are affiliated with CCNY. You'll be able to get a link to the website. You can follow us on LinkedIn. We share kind of all the latest about the center and our industry partners on LinkedIn. And I'll go into our board makeup here in a little bit. The annual cadence, we're about to have our fall industry advisory board meeting on October 28th. I'll share some details about that in a few slides. And this fall meeting is really the first chance for our board to hear about research progress from our research teams. And then we also start setting up the research topics for our next funding year. So we'll kind of query all the guests at the meeting, all our board members about what research topics need to be addressed by the center. In the winter, our faculty at CU Boulder and CCNY will prepare proposals to respond to those research needs. And then in our spring meeting, usually in April, those proposals will be voted on by the board to select which projects will get funding for next year. And then summer hits, we kind of get all the funding awarded, and projects start at the start of the semester in August. So these are the themes that the center is kind of our research is focused on: innovative building materials, This relates directly to what Moncef was mentioning about dynamic facades. So, anything related to, window systems, wall systems. We have projects this year, you'll see in the next slide, around kind of net positive window systems or embodied operating carbon of facade technologies. So that all falls in this innovative building materials bucket. Advanced energy systems. So this is mostly related to thermal systems. CCNY has done quite a bit of good research on heat pumps, and they recently were just awarded a provisional patent on a transcritical CO2 heat pump system. So happy to chat more about that after, if you're interested. Integrated energy generation and storage. I'll describe an example project from that research theme. So this is kind of how do you generate, but also store electrical and thermal energy at a building? How do you kind of design building controls to optimally use that energy? And for example, to shift your peak or shift your energy use to try to avoid increased energy costs from like demand response type scenarios. I'll also share a little bit of research on smart buildings and cities. This is really exciting. Buildings are increasingly becoming more connected, and the building systems within them are increasingly able to talk to each other. So you may, walk into a building and occupancy sensors that are connected to the lighting system could tell the HVAC system to turn on. So there's a lot of opportunities to improve energy efficiency as well as occupant experiences in buildings through making them smarter and more connected. Intelligent grid systems. So this would be kind of on the microgrid, grid interactive buildings topics that Moncef was mentioning. We haven't had a ton of research in this space. We're actively looking for industry partners to join our board and support this research theme. And then the building retrofit tool that Moncef mentioned just before I started talking is an example of one of the research projects around retrofit applications that the Best Center has funded. So here are some of the projects that we're funding for this year. So these are actively being worked on by our faculty and students. I'll go into detail on the project on the top left. Pretty exciting project with a mouthful of a title around using these transparent and highly insulating materials to add thermal storage to a building. But we also have topics around kind of building envelope, embodied energy and embodied carbon, net positive energy buildings or window systems, optimizing air source heat pumps. And the middle on the right project is pretty interesting. It's kind of how do you integrate modern building components that may have some black box controls. So we may not be able to see exactly how these building components interact with a building because maybe they have proprietary controls or AI intelligence on them. So Gregor Henze in the department is focusing on how do you integrate these types of devices into energy modeling and is applying that technology to an adaptive reuse scenario in San Francisco. So one of our industry partners has a building, they're converting from commercial to residential, and they need help analyzing these types of systems to understand the energy performance as that conversion occurs. And you can find all of our executive summaries, some of our research output on our website, best-iucrc.org. And I'm happy to follow up if you have any questions about any of the projects on the website. This is the makeup of our board. So we have a few manufacturers, Rheem for kind of the thermal systems, Belimo for building control components. We have a couple utilities companies, Excel and Con Ed, kind of covering the CU and CCNY regions. A couple glass companies, Cardinal and Alpin. Alpin's located just down the road from us. And they're pretty critical to a lot of our facade window testing research projects. We have a group of engineering consulting firms. So if you're a consulting firm, reach out to us. We're happy to add consulting firms. So we see their input as really valuable because they're interacting directly with the design and maintenance of buildings. And then we also have the City of Boulder involved as an affiliate. Alrighty, and the last kind of Best Center admin related slide is announcing our fall meeting. So we'll have locations, small group meetings in Boulder and New York, but you're also welcome to join on Zoom. This will be on October 28th from 8 a.m. to 3 p.m. Mountain Time. In the afternoon, all of our projects for the current funding year will be presented, but also in the morning, we'll have a keynote speaker from Carrier talking about their vision for the future of energy efficient and smart buildings. And then we'll also have a session where we're brainstorming with our guests and attendees about the research topics for next year's request for proposals. So you can go to our website in the events section, find the registration and additional details on the agenda. So now I'm going to go through in probably just a lighter bit of detail than the faculty could do themselves, a couple of projects that we have funded for this year and then a past project. So this project is with Ivan Smoliak in the physics department. This is a project that's ongoing right now, titled Enhancing Thermal Energy Harvesting and Storage Using Monolithic Mesoporous Metamaterials and Phase Change Materials. And I'll describe what those are, but a lot of acronyms are about to be thrown your way. To motivate why this is important, we're going to talk about thermal energy storage in buildings. So thermal energy storage is a way to kind of, you can think of it as a thermal battery. How do you hold on to heat during that's generated during the day and then release it at night when the sun's not shining and when some renewable sources are not active? So oftentimes this is a neglected technology in buildings, but it is promising. So it can be competitive with lithium-ion batteries as a way of storing energy, especially when your thermal energy storage has high storage capacity. And to improve that storage capacity, we need to insulate the material that is storing energy from ambient temperature. And one of the ways to insulate this material is to wrap it in something that's very insulating. Now that's where these mesoporous monolithic metamaterials come in. They're both highly transparent and insulating. So very cutting edge. Ivan just got a world record, Guinness Book of World Records awarded for this material. So it's over 99% transparent, meaning all the visible light from the sun can get through it. It doesn't impact how you see the light. So the color rendering index is kind of how you perceive different colors in an environment. But it's also very insulating. So it's equivalent to a R15 insulating rating or higher. And it can be very cheaply manufactured. So here you can see on the bottom left kind of an image of that sample out looking at the Flatirons here in Boulder. So very little impact on the way it's visually perceived. Now that lets the light in, and then once that energy comes in, we'll want it to be absorbed by something. So I'll show on the next slide. The project is putting a black body absorber on the face of phase change materials. The black body will absorb all the light and heat from outside, and then it'll transfer that heat to a phase change material. And the nice thing about phase change materials is that they're able to move from a solid to a liquid as they gain heat energy and store that heat energy in the liquid phase until it's ready to be used. So you can see on the bottom right in this figure, we kind of have this solid to liquid cycle of heat being stored and then released. So this is a highly effective way to achieve thermal energy storage. And by coupling this phase change material with a black body absorber and embedding both of those in mesoporous metamaterials, we can achieve a high amount of energy storage. So here's kind of what that looks like. And on the bottom left, you can see an example of how this has actually been tested. So solar energy gets in through maybe a window, travels through the optically transparent monolithic mesoporous metamaterial, gets absorbed by that black body absorber, and then stored in the phase change material. And since that phase change material is embedded in this metamaterial, it's not going to be release that heat until much later than typical. It also acts as a little bit of a greenhouse effect. So you can let in the visible light, absorb it, and trap it in as all the thermal energy. So this allows for energy to be stored for up to 12 hours and really can help with shifting load from when you can generate it during the day to when it's needed at night. Alrighty. So moving on to another project, this will speak to the smart building component of our center. And this is around kind of AI, machine learning algorithms for building control. So to motivate this, as I mentioned, increasingly we have more and more systems connected to buildings, whether these are renewable energy sources, EV charging stations, devices, IoT devices, et cetera. And to kind of coordinate all these systems, we need advanced control systems. Buildings need to meet multiple objectives. So they need to meet energy efficiency, they need to meet indoor quality, thermal comfort, and others. And having these multiple objectives can really be a challenge when a lot of our systems are really just designed to achieve one or two objectives. So typically we'd use rule-based control to control buildings. So this would be, if a thermostat on the wall with a set point, and if the temperature goes outside of that set point, then things change. That's kind of the traditional way, but it's not ideal at doing this multiple objective achievement. So researchers are looking at other algorithms, and the focus here is on reinforcement learning, which is a machine learning approach that can kind of balance these multiple objectives to achieve the goal. And the value in this research is reinforcement learning has a very long training process. You kind of have to use this AI agent to learn how the building operates over time, and eventually it can figure out the accurate control. But in most buildings, we don't have a lot of time to allow one of these reinforcement learning agents to fiddle with the controls and figure out the optimal solution. So coupling these agents with what Gregor is calling surrogate models can help reduce that training time. So they applied this reinforcement learning algorithm to a case study. This is a small office building with multiple zones in Chicago. It's got a constant air volume air handling unit, gas heating, DX cooling, and it's using kind of the industry standard control sequences. It's got a PV system and a battery to store energy and generate energy. And the algorithm is trying to reduce energy consumption cost and reduce thermal comfort and avoid demand response costs all at the same time. So that's where that multiple objective aspect comes in. And the things it can do is change the temperature set point of the zones and discharge the battery. So here I'm going to compare three cases. The classic case of just pure rule-based control. The second case would be pure reinforcement learning. And through the research, they found that you could achieve about 40% lower cost compared to the traditional rule-based control with this technique. And then if you add these surrogate models to improve the training time, you can get a little better performance out of your controls, but you can also achieve it much faster. So here you're seeing on the figure, kind of the number of steps of training required to get these algorithms to be performing well. You can see after like 6 episodes, they're all performing, reasonably comparable. But initially, case 2, pure reinforcement learning, it doesn't know much about the system. So it's having to incur large costs initially and then reduce that cost over time as it determines an optimal control scheme. And then if you add these surrogate models to the system, which are random forest, deep neural network type things that are trying to predict aspects of the building based on pre-known information, that immediately it's better performing and then can perform better over time than just the pure reinforcement learning process. So here's a figure showing that pure reinforcement learning example. On the left, we have the first training day, and really it's just exploring the space in which it can operate. It's really not optimized in any way. And then on the right, you can see the performance on the last day. So on the top figure, it's staying within the thermal comfort bounds. It's even during the peak demand response time, it's reducing the temperature in the space. to try to balance the cost of energy during demand response times. So it's deviating from that set point on purpose. And you can also see it's more intelligently charging and using the battery on the bottom right two panels. And just as a comparison, the case 3, where you add these surrogate models, it's fairly immediately able to kind of understand that it needs to stay within thermal comfort ranges. It can store and discharge the battery much more intelligently right away. And then on the last day of training, it's pretty much mimicking the pure reinforcement learning process, where it's able to maintain thermal comfort, discharge the battery strategically, and then it also kind of dips into that balancing the costs of keeping the space cool while also balancing the battery discharge during the demand response time. So it's able to kind of do that multiple objective need. Yeah, so that's kind of the overview of the BEST Center. I'll hand it back over to Moncef to describe the last building, or the last program.
Great. Thanks, Nick. So as you saw, there's some research activity related to energy efficiency of building. This program, which is funded by Department of Energy, is trying to at least showcase or apply some of these research activity into the real world. So we're pleased finally, after 1 year of negotiation with Department of Energy, we have the, I guess, program ongoing now. So this Renew American nonprofit for Rocky Mountain regions, managed by University of Colorado, is trying to at least to provide technical assistance as well as fund to retrofit facility that are owned and operated by nonprofit within 5 states in the Rocky Mountain region. The program is for 4 years. Ideally, it started in June 1st, effectively, actually October 1st, and then it will go to 2028. As I mentioned, this program is focused on energy efficiency of existing building for nonprofit organization in Colorado, Utah, Wyoming, Montana, and Idaho. So if you know of any nonprofit organization or you're part of a nonprofit organization that would like to have a retrofit done, we could help them at least with the energy analysis, the level 1, level 2 energy audit, as well as provide or at least recommend to Department of Energy to provide fund for them. The objective is to try to reduce for the entire portfolio that we are dealing with the energy cost by 25%, and we hope also to achieve carbon emission reduction by 25%. In addition to University of Colorado, we have partners that help us in this program, including partners related to the recruiting of nonprofit. For instance, Mountain Sky Conference, City of Boulder, for instance, as well as Platte River Power Authority. And we have partners that help us with technical assistance, like Noresco and ICAST, as well as some partners that help with demonstration of some product, like product of Train, Mitsubishi, as well as Alpen. And we are seeking, as I said, partner also to help us with the execution of this program, in addition to the recruiting of nonprofit. How this program works, quickly, for the next maybe 3 minutes or so, is basically we are trying to cover as many nonprofit as possible initially, up to 140 nonprofit facility, even though our model can accept any numbers. So we hope over the 4 years to reach at least 140 nonprofit organization and audit 140 facilities specifically. And based on our analysis, as I mentioned, level 1 and then level 2, we screen all these facilities that allow us to achieve our goal of 25% to about 60 or 40 facility. From those, we'll select about 24 to 36 to fund to actually implement the retrofit measure. And then for these, we go back and actually measure and verify the saving as part of the program itself. So in addition to benefiting the nonprofit organization, we hope to also train our student to obviously conduct all these energy analysis and retrofit measure implementation, as well as MNV applications. University of Colorado is one of two actually university that was awarded among I think 8 or 9 this type of award for the RAN program in the US. So this program almost covered the entire US, shown in the map there, with CU covering the Rocky Mountain regions. Okay. And we can, as I mentioned, this program focus on 4 phases. The recruiting obviously is one of them, and we hope that you help us with this part. If you know of any nonprofit organization that has a facility that benefit from energy audit as well as retrofit, we do in-house, at least mostly, at CU, the technical analysis and assistance. Then we provide at least for some facilities the fund through Department of Energy, obviously, after their approval, up to 200. We all have also some co-share, but the fund from Department of Energy goes up to 200K per facility. So that's why we want to reach as much as possible initially, and then we select about 24 to 36. It depends on the fund, depends on the facility. So we don't know the specific facility that will benefit from these. And then, as I said, at the end, we go back and do outcome analysis through MNV protocol. In general, these programs allow us to actually, especially the students, to see how the research activity can be implemented in real life, okay? As well as doing our outreach to the community in a way. So that's our first phase, and that's why we're reaching out to you as alumni of CU to help us in this outreach in a way, recruiting of nonprofit organization that has at least that own as well as operate their facility. So far, we have about 40 facility at least that apply through our website that I mentioned before, I think. In phase 2, that's where the learning of our students as well as our partner will help, like ICAST as NORESCO, in the technical assistant assessment. And we'll use the tool that I mentioned before as part of our research activity to demonstrate the effectiveness of these kind of tools in doing energy audit, especially make level 1 energy audit more efficient as well as effective. And then in phase 3, that's where we do the selections process of who will benefit from the actual fund to do the retrofit. And the plan here is to make sure we do at least systematic selection process through all these analysis that I mentioned in phase 2. Phase 3 will provide help as the university and its partner. Effectively, the beneficiary or subrecipient, we call them, will manage their own retrofit project, but we'll help them with the scheduling as well as actually the particular selection of subcontractors. And we already have identified some subcontractor that will be at least help us with this project. And then, as I mentioned, phase 4 will be again related to technical analysis using MNV protocols to determine what is really the impact of the retrofit project on the energy cost as well as energy consumption and then carbon emissions. and we'll use, when known, at least protocol to determine these potential saving from the retrofit measure. And again, the student will be trained on doing these type of analysis. So with this, we gave you at least a couple programs that we think our alumni could help us in terms of spreading the world. The best center, as I mentioned, is focusing on the research side of the architecture and engineering program. So any member with the contact, or at least with some connection with the industrial partner could at least share the information we shared with you today about the best center. For the RAND program, if you know of any nonprofit, as I said, organization that own and actually operate their facility, will be happy to at least provide them with the technical assistance and potentially the fund to retrofit their facility. With this, I'll end with obviously note that, as some of you know, CU has been participating for a long time ago, I guess, since the inception of Solar Decathlon, and have won so far 3 at least Solar Decathlon competitions, which is a testament of the quality of our students as well as our program. With this, I'll open it for Q&A, I think. Ellie, is that the next step?
Yeah, thank you so much, Dr. Clements and Professor Krarti, for sharing about your work today. So we'll start with some of the questions that we got with folks' registrations. So to begin, I think this kind of relates to what you were talking about at the end there, but how can students get involved with these projects? What can mechanical engineering students do? And is it mostly research or industry work?
Yeah, actually, as I mentioned, these two programs that we highlighted today involve students, both the graduate level students as well as undergraduate students. For instance, we have a fund to support undergraduate research, especially in our facility, Larson Lab, for instance, HVAC facility, as well as in the best funded project. We have also a fund through NSF, through what they call at least research experience for undergraduate, that include any students at CU, especially engineering students. And we have a couple mechanical engineering students involved in the REU, research experience for undergraduate, as part of the BEST Center. So we encourage and we hope more students apply to both the architecture engineering program as well as to research activity in both the BEST Center and the RAND program, as well as other programs within the architecture engineering program.
Awesome. When designing a building, should embodied carbon or operational carbon be more important?
Of course, yeah. This is a hot topic these days on how to design and even retrofit building, is to take into account both the embodied as well as operation carbon emissions. So, and that's what we started doing as part of as Nick mentioned, as part of the BEST Center funded project. We looked at the embodied carbon in some of the building envelope, so we can help the community use these metric to at least optimize the design as well as the retrofit of building in general. The challenge, obviously, there is a lot of systems, especially building energy system, with limited data about the embodied carbon in these systems. So that's very difficult for the industry in general to take those systematically and based on this limited data to do the design or at least to optimize the design of building. But in the next as I mentioned, this is a hot topic. So in the next 5-10 years, I think the embodies as well as the operations carbon emission will be part of the design process, and LEED already including this as a metric for providing the score in terms of sustainable building rating.
Great. Thank you so much for answering that. I know we're coming to the end of our hour, so if you submitted a question in advance that we weren't able to get to, please don't hesitate to reach out to Professor Krarti or Dr. Clements. I'll be sending an email tomorrow that will have some links and contact information from them as well if you need to reach out. So before we sign off, we would appreciate some audience feedback on the event. My colleague Kevin here is going to launch a poll that you should see on your screen right now, asking you to indicate on a scale of 1 to 10 how likely you are to recommend another CU Engineering alumni webinar, and we really appreciate your responses. Additionally, please be on the lookout for a follow-up email tomorrow, like I mentioned, with a brief survey to share further feedback from this webinar, plus additional information from this presentation, as well as how you can stay connected to the College of Engineering and Applied Science with some of our upcoming engineering alumni events. So I just want to give a huge thank you again to Professor Krarti and Dr. Clements, and thank you to all of our participants today for joining us. We really hope to see you again soon. So thank you. Have a good day.